last week we talked about greenhouses and selecting greenhouses and the things that you need to think about whenever you're going to choose a selection for a greenhouse or a site for a greenhouse. And I mentioned to you that a greenhouse is something in which we control the environment or the temperature. So this week we're going to start looking at how do you know which environmental control to choose. So we're looking at chapter 4B. I would really encourage you to follow along in your book and do some study of this instead of just listening to the presentation. But let's get started. If you're going to raise crops in East Tennessee, it's pretty clear that during the winter months you're going to have some kind of heat source. And when you are looking at a heat source, you want to consider the availability of that heat source, whether it be wood or gas or electricity. You want to consider the economics of that particular heat source. While electricity might be a good heat source, it might be really costly. And then finally you want to look at dependability. Just because something is cheap doesn't mean that it's dependable. So on this slide you'll see that there are several different heat sources that are listed, and you'll see that some considerations for use of each of these is listed, along with the efficiency rating of a few of these. Perhaps the most commonly used heat source is natural gas. It's clean to burn, it's a low maintenance heat source, and you can get about 1,000 BTU, which is a 70% efficiency, which is not a bad efficiency. Not exactly what we would like for it to be, but given the price of natural gas, it seems to be the most commonly used for greenhouses, at least in East Tennessee. A lot of people ask me about electricity. The problem with electricity is that it's expensive. Now, if you were going to have just a small greenhouse at home, it's probably practical for you. But if you're talking about a large-scale greenhouse operation, it's just not worth it. It's too expensive for a month-to-month bill, and it's not usually practical. You'll also notice that solar and radiant heat are listed here. Both of those are alternative heat sources. They might work for you, but depending on the money that you have to put into the initial setup, probably not going to be on your radar. So if you're looking at things that we actually would use in East Tennessee, you're probably going to be looking at the first 6: wood, coal, liquid propane, natural gas, fuel oil, or electricity. And coal in this part of the country is not really readily available. It depends on, I guess it depends on exactly where you live, but really you're probably looking more at natural gas or electricity in some situations. And of course, I'm not going to limit what could be used as heat sources just to the things on the list you saw on that previous page. Pretty much anything that burns, someone has probably tried it. You need to remember that regardless of what you're using, if something has an open flame, it's going to need ventilation. And the last thing here says, this is in terms of ventilation, you need about 50 square inches of open space for each 100,000 BTU per hour of furnace capacity. So if you were asked to calculate how much ventilation space or how much outside air space you would need, you would look at how much BTU per hour you are generating with your furnace and then multiply that by 50 square inches. We also have to look at heat distribution systems. If we just have a heater in the back of the greenhouse, that heat is not evenly dispersed all over the greenhouse. One method is a forced hot air system where a fan jet is installed near the heater and picks up the heated air and directs it down a big plastic tube that runs down the length of the greenhouse. And this plastic tube has holes in it, and so as that fan pushes the heat down this big inflated tube, it will allow some of the heated energy to come out of those holes. Another way to distribute heat is using halve fans or horizontal airflow fans. In this case, each side of the greenhouse you have low volume fans that circulate the air around the greenhouse, and depending on the size of the greenhouse you may need 4, 1 in each corner, or you may need 6, 4 in each corner and 2 in the middle, but you're pretty much just trying to move air from the furnace around the greenhouse. And then the last thing you'll see here is natural air distribution. In this case, hot water or steam pipes are placed along the side walls of the greenhouse. Whenever they're in use, the heated air that's in the vicinity of the pipes rises and follows the slope of the greenhouse to the peak, where it meets air rising from the other side. When these two meet, then they force each other down, and it causes the air to come down towards the plants, and that's just allowing the air to kind of naturally flow from these heated pipes. So today we're going to look at how do we calculate the heat requirements for my greenhouse. If I'm going to start a greenhouse business, how do I know what size heater to purchase? Well, heat required is dependent upon the type of covering or the glazing that you use, the amount of exposed surface of the greenhouse, the desired inside temperature, because if you're growing tomatoes, the desired inside temperature is much greater than if you're growing, let's say, nursery plants. Wind speed in your area is going to be a factor, because the faster the wind travels across the greenhouse, the more heat that wind is able to take off the surface. The condition of the covering. A newer covering holds heat better than an old covering. And then, of course, the outside temperature, and we base that on the lowest average temperature for your region. So we have a formula that we can use to calculate heat requirements. You'll see here that H in this formula stands for the amount of heat required in BTU. K is a heat transfer coefficient. It's going to be given to you. Each type of glazing has a different value for K. So if you were calculating for glass as compared to polyethylene, you would have a different K value, but those are standards that are already set. A is the exposed surface of the greenhouse. T1 is the desired inside temperature, and T2 is the outside temperature. Again, that's based on that lowest yearly average. Now keep in mind that the formula will account for heat loss through the covering of the house through the glazing, but it does not account for heat loss due to high winds, poor condition of the covering, opening of doors, or something like that. So in order to allow for these losses, you'll need to add an extra 10% after we've calculated the heat requirements. So what is the formula, you ask? Well, it's H, or the heat requirements, is equal to K, the coefficient, multiplied by the area, multiplied by the difference in inside and outside temperature. So first you want to subtract the lowest average outside temperature from the desired inside temperature. Then you want to multiply that number by the number of square feet that is exposed on the outside of your greenhouse, and then multiply by the given coefficient K for whatever glazing you're using. Let's assume that you had a greenhouse that was covered with a double layer of polyethylene that was 26 feet wide, 96 feet long, with 4-foot sidewalls and 11-foot peaks. We want to keep a minimum inside temperature of 60 degrees Fahrenheit when the average outside temperature is 40 degrees Fahrenheit. Let's look at how we would find the heat requirements. If we're looking at our formula of H equals Ka times T1 minus T2, we first need to look for K. The way we find the value of K is again from a table that is already given to us. Our example said that we were going to use a double layer of poly. So if you look in this table here, you'll see that K for a double layer of polyethylene is equal to 0.8. This chart can also be found on page 25 of your book if you are needing to calculate heat requirements for another type of glazing. After we find K, we have to determine how to find A, or the surface area of this greenhouse. So we can start, first of all, by finding the area of the sidewall. That would be this blue section here that you see. This blue section here, to find the area, would be the equivalent of 96 feet long times 4 feet tall, or 384 square feet. But you have to keep in mind that we have a sidewall on each side of the greenhouse, so we must multiply that 384 by 2 for a total of 768 square feet. Now if we come to the end of the greenhouse, we'll notice that this area here that kind of looks purple is also 4 feet tall. We can break it off, but it's 26 feet wide. So if we had 26 feet times 4 feet, that would give us 104 feet. Again, we have this area on both sides of the greenhouse, so 104 times 2 is 208. Then for the triangle that you see up here, we already know that it's 26 feet wide. We also know that the length from the peak of the roof to the ground is 4 feet, and that the area from the sidewall down, the length from the peak to the ground is 11 feet, and the area of the sidewall is 4 feet. So from this point here to the top would give us a value of 7 feet. So if we were to multiply this 26 feet by the 7 feet, we would find out the area for this if it were a square. But since it's not, since it's a triangle, then we take half of that. So 1/2 times 26 times 7 is 91 square feet. Keep in mind that we have areas on both sides, so 91 times 2 is equal to 182. Finally, we want to find the area of this yellow part. We know that the length is 96 feet. What we don't know is what the angled side is, or what the height of this is. So we have to use a squared plus b squared equals c squared in order to find this. We've already determined that the length of b would be 7 feet. If we look at a, we take half of 26, which would be 13. So if you'll come over to the side in this yellow box, a is the equivalent of 13 because that's half of 26. B is equal to 7 because we subtracted 4 from 11. If we square both of these, you'll find that you get square of 13 is 169, square of 7 is 49. That gives us a value of 218. So c squared is equal to 218. We must now take the square root of 218 to find what c is, and that is a value of 14.76. So now that we know that that area is 14.76, or that length is 14.76, that would be your value here, we can multiply the length of this greenhouse, which is 96 feet, by the height of this greenhouse, which is 14.76, and get 1416.96. Again, we have two sides, so we multiply by 2 for 2833.92. Now, if we take all of those square feet that we added up, the 2833.92, 768, 208, and 182, we find out that the total area of this greenhouse is 3,991.92 square feet. We can now look at the temperatures. We know that T1, we were given that minimum temperature is 60, and that T2 is 40.
So now that we've calculated all of these values, if we were to plug those values into the formula that we had earlier, we could calculate the size of the heater that we need. So here you'll find that H is equal to 0.8, which was that coefficient that was given to us because we're using a double layer of polyethylene. We take the area that we found, which is 3,991 square feet. Then we take the difference of the desired inside temperature and the average outside minimum temperature. When we multiply all of those together, we get a value of 62,870.72 BTUs per hour. If you've had trouble up to this point, you don't know where that value is from, I encourage you to go back and watch this again, or either look through your book and work on this. If you're still having trouble, be sure you give me a call, because this week's assignment will require you to do some calculation. Now, since some heat is lost due to winds or doors that open or whatever the case may be, we usually add 10% to allow for that. So to add 10%, we want the total BTU per hour times 110%, because anything over 100% would give us that extra 10%. So if you multiply 62,870.72 times 1.1, we find out that we really need 70,257.792 BTUs per hour. However, most furnaces are not 100% efficient, so once we get to this point, we then have to consider the furnace efficiency. If we have an 80% efficient furnace, we would take the required BTU, divide by 0.8, and find out that when we purchase the furnace, we need to buy a furnace that is 87 87,822 BTU capable, which means we're probably going to be looking at about a 90,000 BTU furnace, just because you can't get a furnace that's 87,000 BTU. Generally those come in increments. So keep in mind that once you find the required BTU, you must allow for loss, which is generally 10%, so we multiply by 1.1. Then we divide by the furnace efficiency, because we know that not all furnaces are equal.